So today I want to talk about a work that I did with Alexis, Arnaudon, and Alessandro, Barp on constructing a certain Monte Carlo algorithm to sample from target distributions on Lie groups. So I think a lot of people have this experience before where you started off with some project and you ended up doing something completely different. So that was what happened with us. So when we started off the project, we never intended to work on Lie groups at all. So what we did initially was we wanted to construct a Monte Carlo method based on a stochastic Hamiltonian systems. And long story short, we sort of rediscovered this thing called the generalized HMC algorithm, which apparently was well known like 30 years prior to this. So we had to think of some ways to do some new stuff. And because all of us came from a sort of a geometric mechanics background, well, we thought, okay, well, why not extend this generalized HMC algorithm to manifolds, and then just submit it to GSI. So it turns out that extending this to manifolds, to construct a practical GHMC method on manifolds is a tricky issue, but you can do this for Lie groups. So that's what I'm going to talk about today. So to motivate this thing, a lot of times we're faced with the problem of evaluating the expectation of a function with respect to some measure. And often in statistics, your parameter theta tends to be living in a really high dimensional space. So when you try to approximate this integral directly with brute force, then chances are that you won't live to see your result. So if you want to see your result within your lifetime, what you have to do is you have to come up with an alternative approach to approximate this integral. And one popular way to do this is the Monte Carlo method. So Monte Carlo method is basically, it's like a kind of clever way to sample random points in your underlying space, such that the distribution of your points approximate the target measure that you want to draw your samples from, so that if you sum over the functions evaluated at these points, then it should approximate your integral fairly well. So that sounds easy, right? But then the problem is, how do we sample these points? So one way to do this is called the Langevin sampling, where you use the property of the Langevin stochastic differential equation, which has the property that your invariant measure is given by the following. So it's like e to the minus the Hamiltonian. And if you choose your Hamiltonian to be equal to minus the log of the target distribution, then you see that your target measure is preserved, like the pi x dx. So then if you run your Langevin system for a sufficiently long time, and then you use the ergodic property of your Langevin system, then you should be able to approximate your expectation fairly well by using this, by summing over the function evaluated at some random points of your trajectories of your Langevin system. So initially when we started this project, we kind of wanted to extend this. So what we did was we considered this stochastic Hamiltonian system, and we wanted to construct a Langevin sampler that had a multiplicative noise, so that you can kind of control the size of your noise depending on where in phase space you are. So the question was, what can you add or subtract in order to keep your canonical measure? So canonical measure is this e to the minus Hamiltonian multiplied by the Lebesgue measure. So when is this invariant? So after doing some computations, it seems like this works, where the bracket here is given by, this bracket is called it's a Poisson bracket, it's a canonical Poisson bracket. And if you add this, then it preserves the invariant measure. So the consequence of this is that if you choose your Hamiltonian to be the typical one, it's the sum of your kinetic energy plus the potential energy, where your potential energy is given by minus the log of the distribution, then if you decompose your canonical measure into your position part and your momentum part, then if you project it down to the position part, you see that it preserves the target measure. So we thought that, okay, maybe we can use this sort of Hamiltonian Langevin system to create a Monte Carlo method that samples from this target measure. But then apparently, well, there was a lot of difficulties associated with this, like from a numerical point of view, and we couldn't really do much with it, and we couldn't really get an interesting result. Except with this special case when we chose our noise Hamiltonian. So this is the Hamiltonian that generates the noise part, to be of the special form. So actually it works if you just have a general Hamiltonian that depends on the position. But if you have this noise Hamiltonian, then your Langevin system that I just showed you takes this form. And the nice thing about this is that, okay, so this is you can think of this as into two parts, which is first is the Hamiltonian part, and the second is an Ornstein-Uhlenbeck process. And the nice thing about Ornstein-Uhlenbeck process is that you have an explicit solution. So if you want to compute the momentum P at time h, it's equivalent to basically just drawing a random sample from the normal distribution centered around this mean that depends on the initial condition of your momentum with some variance. And this turned out to be the basis of what was called the generalized HMC algorithm. So what the generalized HMC is it's basically a numerical splitting of the Langevin system that I showed you into an OU part and a Hamiltonian part, and then followed by some kind of a Metropolis-Hastings acceptance rejectance reject step. So here you solve your OU part explicitly by drawing this random sample from this normal distribution, and then you solve a Hamiltonian part, and then you do this Metropolis-Hastings step. So what is different from the HMC is that in HMC, your first part is you're basically drawing your momentum from a standard normal distribution. Whereas here, you are drawing from this distribution here, this normal distribution with mean centered around your momentum, and then basically retains some partial information about the current value of the momentum that you have. So the generalized HMC is sort of like a partial momentum refreshment compared to the full momentum refreshment in the standard Hamiltonian Monte Carlo method, which gives an advantage, like it converges to the target distribution faster and so on. So we wanted to extend this to manifolds. But before that, let me just show you some like a pictorial explanation of how this thing works. So the question is you want to sample from this target measure pi. So in the first step of the GHMC, you just initialize your position and momentum. So just choose a random point and your momentum in the phase space. And then in the second step, you integrate your Hamilton's equation of motion until some time, like tau, it doesn't really matter, where your Hamiltonian is given by the sum of the kinetic energy plus the potential energy, where your potential energy is given by minus the log of the pi. And then when you discretize this, of course, you can't exactly integrate your Hamiltonian system, so you have to rely on some kind of numerical discretization. And the leapfrog scheme is usually the popular one, but you can use any symplectic integrators to solve this part. So then if you run this, you get a new proposal for your Monte Carlo step. And then after you got your new proposal, you basically accept or reject your proposal with some probability alpha. And intuitively speaking, this is kind of like correcting for the numerical error that was introduced in the step 2 when you integrate your Hamiltonian system using some numerical scheme. So then if you accept your proposal, you keep the current proposal, the new proposal, as a starting point for your next iteration. And then if you reject, you go back to your old proposal in the next iteration, but you flip the momentum. Okay, so then now you have to kind of distinguish between the HMC and GHMC. So then let's say that your new proposal was accepted, and then we want to iterate this again. So in the generalized Hamiltonian Monte Carlo method, in the next step, you solve for the OU equation by sampling from this momentum, which is given by the normal distribution centered around this, the mean and the variance. So this contrasts with the standard HMC, where you would just do a full momentum refreshment. So that's pretty much the only difference with the generalized Hamiltonian Monte Carlo and the standard Hamiltonian Monte Carlo. And then you run your Hamiltonian step as before, and then you apply the Metropolis-Hastings step, and then here it was accepted. And then you basically continue this cycle of solving the OU process, and then you solve the Hamiltonian system until you get more points, and you get more points until you're satisfied. So that's how it pretty much works, okay? So is that okay? So now let's go back to the Langevin system that I just considered. So we wanted to extend this to more general manifolds than just in the Euclidean space, because we only looked in the Euclidean space for now. So if you're sort of familiar with geometric mechanics or in Hamiltonian systems, you will probably be asking, because this system only depends on the Hamiltonian structure, like the Hamiltonian and the symplectic structure, why can't we just generalize this to symplectic manifolds or just like cotangent bundle, for example? So that's what we did, and we got this equation, which is just like we just rewrote this equation in this, how do you say this, non-coordinate form, the coordinate-free form, where your XH is the Hamiltonian vector field, and your HIs are your noise Hamiltonians. And then we claimed that this equation on the cotangent bundle has the sort of same properties as the Langevin system that we just considered on the Euclidean space. So let's look at this further. So again, first of all, you can split this equation into a Hamiltonian part. And this is a bit harder to see, but if you choose your noise Hamiltonians to be only dependent on the position, then you can write your equation like this if you choose the Darboux chart. So in Darboux charts, you can write it like this. And this is basically the OU process because your Q is basically fixed, so it's an additive noise, not a multiplicative noise, and you can solve this explicitly. And then furthermore, your canonical measure, so if you do some calculations, you can show that your canonical measure is preserved. So in this case, your canonical measure is given by the exponential of minus h multiplied by the symplectic volume form. The symplectic volume form is just the natural volume form on a symplectic manifold. And then if you project this down to your base manifold, you can show that the target measure is preserved. So the target measure here is the target distribution multiplied by the Riemannian volume form. So you would expect to use this equation to sort of construct a Monte Carlo sampler, so like a Langevin sampler on cotangent bundles or like symplectic manifolds. But then there were some issues, which is that because we're working with manifolds, we have to you have to transition between coordinates. And because we're working with the Darboux charts when we solve the OU process, and for a given symplectic manifold, we don't know what the Darboux charts are. So there's a challenge from a practical point of view. So even though from a theoretical point of view, you can basically do the same kind of thing where you solve for the OU process on the tangent bundle or the cotangent bundle, and then you run the Hamiltonian system followed by the Metropolis-Hastings step to do this generalized Hamiltonian Monte Carlo on your cotangent bundle. But from a practical point of view, it's a bit difficult. So this is basically me when I discovered this issue. And we had to do something with this. So then here comes Lie groups. So the thing about Lie groups is that it's very nice. It has a canonical vector space, which is you call the Lie algebra. And there's something really nice called the Maurer-Cartan form, which associates to each vector on the tangent space a vector on the Lie algebra. So what that does is that you can basically form an isomorphism between your tangent bundle and the space, the Lie group, cross the Lie algebra by this, this map here. So this kind of gives us some hope that instead of solving the OU process on each tangent bundle, the cotangent bundle. So I'm kind of identifying the both things because we're working with a group with a Riemannian metric. Then we have a Riemannian metric, you can identify your tangent and the cotangent bundle by the Riemannian metric. So I'm treating this as the same thing. So then you can hope to solve the OU on the Lie algebra, and then you run the Hamiltonian system. So this was the equation of the sort of the noise plus dissipation part of your Langevin system on the tangent bundle, the cotangent bundle. But then when we use the Maurer-Cartan form, and by doing some calculations, we can show that the system reduces to something like this. And what this is, and so this is exactly the OU process on the Lie algebra. So now we have an idea for a GHMC algorithm on Lie groups, which is that, okay, so in the cotangent bundle case, on a general manifold case, we had the issue where you have to solve the OU process on each cotangent bundle, and then you solve using charts and stuff. But for Lie groups, you can essentially just solve the OU process on the Lie algebra by just sampling from this distribution. So this is the exact solution to your the OU process. And then we solve the Hamiltonian part. And then if you choose a matrix Lie group, you can use the matrix coordinates and there's an algorithm that calculates the Hamiltonian system for you. So for matrix Lie groups, you have a practical and efficient way to sample from your target distribution on Lie groups. So let's see this in action again. So, okay, so I drew a sphere here, but, okay, so Lie groups, sphere is not a Lie group, but I always imagine manifolds as spheres, so that's a Lie group. So we want to sample from the distribution pi. So again, the first step is we initialize the position and momenta on the Lie algebra, okay? And then basically by the Maurer-Cartan form, we can identify this vector with a vector on the Lie algebra, sorry, on the tangent space at the point that we initialized. And then we integrate the Hamilton's equation until some time, the usual thing. So then we do this, and we have a new proposal. And then we accept or reject using this probability. So then if you accept, you start with a new proposal as the new starting point. And if you reject, you go to your old proposal and you flip the momentum as usual. And then you basically, again, you identify your vector with the vector in the Lie algebra, and then you continue. So now, if you want to use the Hamiltonian Monte Carlo method, you would do a full momentum refreshment, whereas if you want to do the generalized Hamiltonian Monte Carlo, you would do a partial momentum refreshment. So you sample the new momentum, you identify with some vector in your in the tangent space, you run a Hamiltonian system, and then you accept and reject. So then you continue this until you get more points, until you're satisfied. So here is an example that we did on the rotation group. So because we don't have much time, I'll just try to rush through this. So we compared the HMC algorithm on SO3 versus the GHMC algorithm on SO3. So in the right figure, I plotted the convergence rate to the target distribution for the HMC versus GHMC on Lie groups. So the HMC is given by the black line, and we see that it performs the worst out of all the cases. So H is just a parameter telling you how long you integrate the OU process, and if H goes to infinity, that tends to the HMC algorithm. So if you take your value of H lower and lower, you see that it performs better. So it converges to the target distribution faster. Oops. It converges to the target distribution faster. But then if you take it too small, like H equals 0.01, then it starts to perform bad again. So you have to do some kind of tuning to get an optimal convergence rate. And the reason why we think that the GHMC works better than the HMC is because GHMC is a non-reversible algorithm, which means that the law of the process that is going forward in time is different from the law that is going backward in time. And then it is often observed that such processes converge to their target distribution faster. So that's pretty much what I wanted to say. And this is just a generalization that we're currently working on right now, but I think we're out of time. So yeah, so thanks for your attention, and here's some references.